became an ordinary person by studying hard would get to be able to imagine these things like I imagine. Of course.
Right, so I want to know how far something moves. That's the change in displacement. Right? Now, how would I know that? I need to know how fast the object's moving and how long it's moving for. Right? So how fast its object moving is the velocity, but it doesn't need to be constant. We could say the average velocity and how long were you traveling. Okay, and so that's a simple equation, but it requires a lot of steps. You know, I'm usually not going to be given what the average velocity is in a problem, so I could say, well, how would I calculate the average velocity? Well, the average velocity, it turns out, is just the average of the starting velocity and the ending velocity. So the starting velocity is v naught, the ending velocity is v, and so to average them, you add them together and divide by how many there are, 2. So this is true. You know, you could prove it using calculus if you feel like it. So that means that if I take this and I can plug it in to this equation where I have v average up there, that means that the change in position is equal to v average, but I'm going to write this new expression, v naught times v over 2 times t. Okay, so that might be useful if I know the starting and ending velocities and I'm given the time, but usually I'm not given that. Usually I know the acceleration, right? So I want to be able to write this knowing only the starting velocity and the acceleration. How far did I go? Okay, so then that means that I don't want to have the ending velocity as part of that. So that's fine because I already have an equation for the ending velocity. So the ending velocity is given by our other kinematic equation, the velocity kinematic equation. So how fast you're going at the end of the motion is given by the starting velocity plus the acceleration times time. Right, so if I insert that into the equation for the displacement, that gives me delta x is equal to, okay, so rather than having this big fraction here, I'm going to pull out that 1/2 in front. So I've got my v naught there still, and then plus, rather than writing v, I'm writing v naught plus at. And that's the end of that big fraction, and that whole thing is still multiplied by time. So let me simplify this a bit. I've got a 1/2 here. I've got a v naught plus a v naught, that's 2 v naught. And then I've got a at in there. And then that's all still times t. So now I'm going to multiply everything through. So I multiply through by the half and the t. So that's going to give me v naught times t plus 1/2 at squared. V naught times t plus 1/2 at squared. That's my change in displacement. Now, a lot of times you'll see this written as final position. Well, okay, so let me write that. The change in displacement is final position minus initial position is equal to v naught t plus 1/2 at squared. And so to write it in the way that you'll usually see it in the textbook, I move the x naught to the right side. So I've got my final position, x, is based on where I started, plus how fast was I going at the start of the motion times time, plus 1/2 at squared. Right? And so that's my displacement kinematic equation, which we can use to solve for any problems. You can use it to solve for the final velocity, or if one of these other variables is your unknown and you know everything else, you can use algebra to manipulate it. So that's an algebraic derivation, an algebraic way of figuring this out. I'm also going to show a geometrical way to understand this. So distance, or change in displacement, is a velocity times time. Right? It's a velocity times time, but what if that velocity is changing? How do we deal with that? That's the whole issue here with kinematics, because this is a problem that you probably could have done in middle school, maybe with different notation, but when that velocity is changing, how do we deal with it? Right, so I showed one algebraic way to get that equation together, but let's think back to when you first learned about multiplication. How do you multiply? Well, you would say, well, what's 2 times 4? You probably were taught to visualize it as, well, it's a rectangle that's 2 squares across and 4 squares long, and 2 times 4 is going to give you 8 squares. So multiplication has something to do with area. And that's a real thing, and it can be used even when you're not dealing with something that's quite that simple. So let's take a look at this plot of velocity versus time here. And this plot of velocity versus time, if I can trace that out, that's a straight line velocity plot, right? So that means that we have a slope to it. That means that there's an acceleration. We start with a velocity of v naught. We end with a final velocity of v. And it's divided into these two parts, right? So if we think about this area of this pinkish square here, well, or rectangle, the one side of it has a length of v naught, and the other side has a length of time, right? So that's going to give me, if I'm the area of that is v naught times t. So you could think of that as how far would the object go if it just traveled at that initial velocity. But now we have an object that is speeding up, right? It's got a positive velocity with a positive acceleration. It's speeding up, so it goes farther than that. So how much farther? Well, the distance from here to here on this blue triangle is the change in velocity. right? It's the distance between v and v naught. So that's v minus v naught, which is equal to acceleration times time. So now we have a triangle who's got a base of length t and a height of length at. And if you remember, the area of a triangle is 1/2 base times height, so that's going to give me an area of 1/2 at squared. So if I think of this, the area of this whole pink plus blue sections is my change in displacement, I can say the change in displacement is equal to v naught t plus 1/2 at squared. Okay, so hopefully either by algebra or by geometry, I've convinced you that this equation is something that we can use going forward.